In this video, we're now going to be exploring geometric series. So now we want to add all the terms that belong in a geometric progression. So for example, this one over here, you can see that it is a GP because to go from one term to the next, we're timesing it by 3 every single time. So the formula for the sum of a geometric series, there's actually 2 of them, is given by the following. We have Sn, remember that S stands for series or sum, and then the subscript n refers to how many terms you're summing from the sequence. So S10 would mean you're adding the first 10 terms of the sequence. So if you look at this formula, we have a bracket r to the n minus 1 over r minus 1. And the second formula just underneath it is very similar. It's Sn is equal to a bracket 1 minus r to the n close bracket over 1 minus r. Now, when you study these 2 formulas, do you notice what is the difference between the 2? They have a lot of similarities as well. You can see that they're essentially the same thing, except the 1 and the r is switched around. And what teachers or the textbook usually says is that if your common ratio is greater than 1, then you would use the first form. If your common ratio is less than 1, then you would use the second form. But I'm going to be honest, you can just stick with one formula regardless of the ratio and you will always get the same answer. Okay, now the intuition behind which one to use, depending on, whether it's greater than or less than 1, is you kind of want to think of always keeping your denominator positive. So if the ratio is greater than 1, let's say r is equal to 2, and you plug it into here, you're going to get 2 minus 1 in a denominator, which stays as a positive 1. But if I sub in r is equal to 2 into the bottom denominator, do you see how it gives you negative 1? 1 minus 2 is negative 1. Okay. But like I said, it truthfully does not matter. So let's go ahead and apply it. Example 1. Find the sum of 10 terms of the following series. So over here in this sequence, you can see that the first term, a, is equal to 3. The common ratio is 5. And we're looking for the sum of the 10 terms. So that means n is equal to 10. So if I plug this into the Sn formula, like I said, I'm always just going to stick with one formula. The formula that I tend to stick to is the first one, where r is first, like it's r minus 1. So this is going to be Sn equals to a bracket r to the n minus 1 over r minus 1. This will become 3 bracket 5 to the power of 10 minus 1 over 5 minus 1. Okay, and this gives us 7,324,218. Okay, now you might be thinking, gosh, that is a huge number. I'm only adding 10 terms here. How did it become 7 million? Well, when you have geometric progression, you're going to notice that the numbers increase massively because in this case, the common ratio is 5. If I were to write down, I don't know, let's say the next 3 terms, I'm going to times this by 5. 75 times 5 is 375. Times that again by 5, we get 1,875. Times that by 5 again. So you can see that the numbers increase so much more. So if you wanted to find, let's say, the 7th term, you might be thinking, oh yeah, it's still quite close to the beginning, but no, it's going to be quite large. Okay, great. Next, we want to find the sum of the first 10 terms of this sequence. So a is 2/3. Now, what's the common ratio? If I go from here to here, how did we do that? Now, if you're comfortable with fractions, you might be able to recognize that we times it by -3 on 2. But if you're not, what you can do as like a foolproof method is to find the common ratio. You take the second term, you divide it by the first term. So T2 divided by T1. So that is going to give you -1 divided by 2 on 3, which just gives you -3 on 2. And the number of terms is 10. So S10 is going to be equal to a bracket r. Now r is negative, so make sure you chuck that in brackets because the power is going to affect whether it becomes positive or negative. So in this case, since n is equal to 10, it's going to keep it positive. So we can go r to the n minus 1 over r minus 1. That's going to give you -15.11. Okay, example number 2. Evaluate the series -3 plus 6, -12 all the way to 384. Now, if I want to add up all these terms, it's clear to me that I have to use Sn, but if I were to plug it into the Sn formula, we're going to get a r to the n minus 1 over r minus 1. I can see that a is going to be negative 3. The common ratio is going to be negative 2. Negative because we're alternating plus minus plus minus. But do we know how many terms there are in this sequence? No, we don't. All we know is that the last term in the sequence is 384. For all we know, we could have 10 terms in this sequence, we could have 15 terms, but it's hard to tell. So what we have to do is we need to actually let the last term in the sequence equal to the Tn formula, the nth term. So we're going to let Tn equal to 384, and we're doing that so that we can figure out what is the n value that corresponds to that. So the nth term formula for geometric progression is ar to the power of n minus 1. We're going to let the nth term equal to 384. A is negative 3 and our ratio is negative 2, making sure you put it in brackets. And then that's going to be to the power of n minus 1. So now we're going to solve for n. First, we're going to divide it by negative 3. We get negative 128 equals to negative 2 to the power of n minus 1. And then I'm going to use logs. So this becomes n minus 1 equals to, now here we have to be a little bit careful, because if I actually do the log method, you can't actually take the log of a negative. So instead, I'm actually going to do some trial and error. So if I do trial and error here, let's do minus 2 or negative 2 to the power of 8. Okay, or I'm going to try negative 2 to the power of 7. So when I do negative 2 to the power of 7, that actually gives me negative 128. So I'm going to then rewrite this in terms of a base of negative 2. So this becomes negative 2 to the power of 7 equals to negative 2 to the power of n minus 1. And then now that this is written in like the same form, we have the same base, which means that the powers must be equal to each other. So we get n minus 1 equals to 7 or n equals to 8. Beautiful. So that would be like our next line of action if we can't take the log of a negative. Okay. Next, example 3. Find an expression for Sn and hence approximate S30 correct to 4 significant figures. Okay, so first let's find an expression for Sn and then we want to find S30. So let's lay down everything we know. A is 1. Our ratio to go from this term to the next term, it's going to be 1.02. So Sn in this case is going to be given by A, or 1 bracket R to the power of n minus 1 over r minus 1. And then now we want to find S30. So if I replace all the n's with 30, we get the following. So this is going to give us 40.57 correct to 4 significant figures. Okay. Now remember that significant figures are different to decimal places. Significant figures also include the number before the decimal. So we have 4 significant figures over here. Great. Next, B. So if I want to find S30, we have A is 3. Now, what's our common ratio? Well, we're going from 3, and then we go to negative 3 root 5. And then we go to 15. So the only way for that to be the case is that for our common ratio to be negative root 5. How we're able to go from a surd and back to a whole number is because when these two surds, root 5 and root 5, multiply each other, the surd or the square root goes away and it just becomes a 5, which makes sense because 3 times 5 is 15. All right, so that means our common ratio is negative root 15 and we're looking for S of 30. So S30 equals to A bracket R to the power of n minus 1 over r minus 1. Okay, now to 4 significant figures, I actually end up with a value that's in scientific notation. So it's going to be negative 2.829 times 10 to the power of 10. So a very, very large value here. Great. Next, example 4. A GP has a common ratio of negative 1/2 And the sum to 8 terms is 425. So let's write that down. The common ratio is -1/2 and the sum to 8 terms is 425. Find the first term of the sequence. So it looks like here that we have all the information we need to actually sub it into the SN formula, but then we're going to have to rearrange it to find our unknown variable A. Okay, so if I plug it in, we're going to get, let's just write down the formula first. All right, now let's plug in what we know. SN, the sum itself is 425. A is what we're looking for. Our ratio is -1/2. Now what's the value of N? It says over here that when you summed 8 terms, you get 425. So that means our N is 8. Minus 1 over R, which is -1/2 minus 1. Okay, so now we want to continue rearranging this until you get the first term, A, as the subject. So I'm going to multiply this over to the other side. So 425 multiplied by, now if you combine this, it's just -3 on 2. So if you multiply that, we get -1275 over 2. And this equals to A, multiply this big bracket. Okay, and then now the last step, if I want to make A the subject, I'm going to get rid of this whole thing that's multiplying to the A, so I'm going to divide it. So if we divide those two big things together, we're actually going to get a lovely value of 640. Okay, so example 5, find the value of N for which the series 2 plus 6 plus 18 exceeds 300,000. Now, we're looking for what term number is the sum of all these values going to first exceed 300,000. So it may be after the 10th term, when you add up the first 10 terms, it exceeds 300,000. So that means N is equal to 10. So let's write down what we want. So we want the N when A is equal to 2, our ratio is 3, and we want the sum to exceed 300,000. All right, so first let's find an expression for the Sn. We're going to get Sn equals to A bracket R to the power of N minus 1 over R minus 1. Now, if you actually simplify this, you're going to see that the 2 at the top and bottom cancel because 3 minus 1 becomes 2. So you just get Sn equals to 3 to the N minus 1. Now we're going to let Sn be greater than 300,000. Now, whenever I do this, I kind of think about it like substituting it in. So I'm going to sub in that Sn equals to 3 to the N minus 1. So it's going to appear on the left-hand side of the inequality. So 3 to the N minus 1 is greater than 300,000. Or 3 to the N is greater than 301,000. And then now if we convert this into a log, we get log to the base 3 of 301,000. Not 301,000. 300,001. Okay, so we get N is greater than log to the base 3 of 300,001 all over log base 3. So we get N is greater than 11.48 ... Now, if we follow this inequality sign, N has to be greater than this number, the integer greater than this, so it's going to be 12 terms, or when N is equal to 12. Okay. Now, it's always a really good idea to test if this is true. So if we substitute N is equal to 12 into our Sn formula from before, now it already simplified, so let's just put it in this more simple form. 3 to the power of 12, if I minus 1, that is going to give me 531,440, which does indeed exceed 300,000. But is it the first term to exceed 300,000? So let's plug in the value before it, which is N is equal to 11. So if I plug in 3 to the power of 11 minus 1, oh, what a funky 3. 3 to the power of 11 minus 1, I actually get 177,000, which is less than 300,000. So that means this is indeed the correct answer.